This is Alice, and this is Bob. This is the evil mailman who wants to read Alice and Bob's letters. To prevent their privacy from being invaded, Bob buys a padlock box and key and sends the padlock and box to Alice, keeping the key for himself. Alice buys her own set of keys and a padlock before locking one of the new keys with Bob's padlock. Bob gets the box, opens it with his key, and now Alice and Bob have the same keys. Alice can send mail to Bob, locking the box with her padlock, and Bob can open the box on the other side, receiving Alice's message securely regardless of the evil mailman's interference. And this is how data is sent between two parties in the real world. Alice could be a computer and Bob a server. The mail they're sending is data, and the keys are long lists of binary numbers that encode and decode the data. But what if a cyber terrorist was able to hack the key? They'd get access to loads of valuable data. And this is a major problem in computer science, especially because sometimes it's not obvious that the key has been hacked, and so the corrupted one continues to be used. Luckily, quantum mechanics and the EM spectrum offers a solution. By converting a photon's polarization, the direction of light oscillation, to zeros and ones, say zeros for vertical oscillation and ones for horizontal oscillation, you can create a completely randomized key. And if someone tries to intercept the key, they tamper with the polarization of the photon, and therefore leave behind a trail that can be tracked. If the user discovers a key has been intercepted, they can simply resend a new key. There are two ways to send these photons, either through fiber optic cables or through a laser pulse that is beamed across open space. The frequency of the laser could range from 300 GHz to 30,000 THz, or from an infrared waves frequency to an ultraviolet one. The exact frequency varies from experiment to experiment because they're each testing different things. While these transfer methods have not been tried on a large scale, Pan Jianwei and his group at the University of Science and Technology in Hefei have used a satellite to link two laboratories more than 1,200 kilometers apart. The satellite shot pairs of entangled photons to both of the lab. Entangled photons are photons whose properties are direct opposites of each other, which means that if one is red, the other is blue, and if one's polarization is vertical, the other's must be horizontal. This property holds no matter how far away they are from each other. When the labs recorded their photons' polarization, they managed to generate the exact opposite keys. But the application of this encryption method is not unprecedented. In 2007, Switzerland attempted to protect the citizens' in-person voting ballots by sending them to the government's central data repository through a quantum connection via fiber optic cables. There's a high possibility that something like this could be implemented in the near future, and this is not as far away as one might think. There's a company in Boston, Raytheon BBN Technologies, that is making superconducting circuits needed to create, manipulate, and detect single photons for encrypted voting. Quantum voting on a large scale could be the next big thing, and all thanks to photons and light.